Welcome back to the classroom. My name is Mr. Wong. Today we're continuing on Module 5, Advanced Mechanics. We are starting the inquiry question 2, circular motion. So all things that move in circles. Let's begin. All right, just to reintroduce you to the syllabus outcomes, we are looking at this syllabus outcome for today's lesson. So solve problems and models and make quantitative predictions about objects executing uniform circular motion with these values that we have here. Okay, we are looking at circular motion. All right, so the lesson intention is to identify an object is circular motion is accelerating. So we'll look into what that means. Your success criteria is to analyze factors that affect an object's circular motion. So let's begin. Okay, so these are some of the formulas we will look into. We won't look at all of them today, but we will briefly talk about velocity, centripetal acceleration, and centripetal force. All right, so the concept of uniform circular motion, what you can actually see here is the object is, and then we'll talk about it in a second, but the concept of uniform circular motion is the object is moving in a perfect radial path and the speed on the circular object remains constant. But what you can see in the motion already here is if you were to cut the motion short and break it apart, it just keeps moving straight. So what's actually happening here when we actually draw out our circular motion, and I might just skip to a different screen, but this is what actually represents uniform circular motion. So you can actually see during that rotation, the velocity is same. It's still 25 meters per second. You have constant speed. However, the direction of the motion is always a tangent to the circle. So don't forget the golden word, tangent, meaning by drawing a straight line on the curvature of the circle at any point. That is the motion of the object. So uniform circular motion, the velocity is constant, but what you can see here is direction is changing. So if we have a constant velocity but a changing, or constant speed to be exact, and a changing direction, then we have acceleration, because acceleration depends on if the speed changes and whether the direction changes. If we have either one, we get acceleration. Now, what's actually happening in circular motion is there is a force pulling it in. Okay, to be exact though, this force is called the centripetal force, and it's not actually a real force. We'll get into why that is the case in a second. Okay, so uniform circular motion is an object that's moving at a constant speed. However, its velocity is changing because there is a change in direction. Okay, so due to a tangent in its curvature or due to a change in direction. Okay, the reason why it accelerates or why the direction is changing is because there's a force pulling the object in. To be exact though, this is a resultant force. So what we call the centripetal force is a resultant force, a combination of all these different forces that add up in a way where the sum of the forces is to pull the object in. Okay, what that actually means is the centripetal force is not actually real. So what we say, like electrostatic forces, gravitational forces, magnetic forces, those are real forces. Centripetal force is not a real force. It's the resultant of all these different forces added together. It just so happens that we use this to describe the resultant force pulling an object in. Keep that in mind. Okay. All right. And we will look into examples as to why that's the case, but I'll give you a really nice example with these two diagrams here. If you think about a car that's rotating around a roundabout, the reason why it can rotate around is because there is a centripetal force pulling it in. Okay, that's kind of the explanation there. But what is the type of force this car is interacting with? It's actually interacting with the friction on the road. So the reason why the car can move in circular motion is because the resultant friction force pushes it inwards. What about a satellite? Okay, it is experiencing a centripetal force, but the thing that causes the satellite to rotate around, let's say, our planet, is actually gravitational force. So this is what I mean by centripetal force. It's a resultant force. It's not actually real. All right, so let's go into now trying to work out how fast an object's circular motion is. So how could we actually work out how fast is something rotating? Well, the first thing is you can work out the total time, or the period. So the time taken it for one revolution to occur. So we know that the number of revolutions divided by, or the total time of the revolutions divided by the number of revolutions will give you the time it takes for one revolution to occur. That's known as the period. We also know when it comes to the rotations, or the quantity of rotations we get per second, we can call that the frequency. So how likely is that going to occur? From year 9 and year 9 waves, and also from the wave topic from year 11, we know that period and frequency are inversely proportional to each other. So that's how you find the two of them. So how could I work out the speed of an object that's going in uniform circular motion? How could I derive that? Okay, what I want to show you is this circle here. Okay, the distance required to move around a whole circle is given by its circumference. The circumference is 2 pi r. Okay, there's that. Now the formula for velocity in normal kinematics is displacement over time. The reason why we're using this formula is we're assuming that at least the speed here is not changing. So that's the idea. Okay, so the distance to travel, displacement, can be replaced as 2 pi r over little t. Now little t represents the time taken for the motion. It doesn't really represent the revolution. So we can just change it around and write this: 2 pi r over capital T, the period, v. And that is how we can calculate the speed of an object going in uniform circular motion. All right, so there are some questions here for you to trial out. Now, just to ensure that this video isn't too long, I am going to skip through these questions. I will make a separate video explaining how to do each of these questions later on. So off we go to the next part of this slide. Okay, the next bit we need to talk about is centripetal acceleration. So we know that objects undergoing uniform circular motion, whilst their velocity, or I'll say that again, whilst their speed is the same, the object is constantly changing still. Its velocity is different, okay? And to represent that, if the velocity is not the same, or is obviously changing, then that means there must be some form of acceleration. So we're going to now look at how we can derive an equation to represent an object undergoing centripetal acceleration. Okay, so what we need to do is understand how we can actually derive the formula for centripetal acceleration. If you find this bit difficult, that's okay. You can just look into the formula, but just to give everyone a little bit more context of how we get these formulas, I'm going to show you how to derive it. So acceleration is just another example of a vector subtraction or substitution. So the direction of the change in velocity is towards the center of the circle. This is also known as the acceleration. Okay, so if you actually have a look, centripetal acceleration is coming towards the center here. Well, as a matter of fact, if I compare the velocities at 2 points, we'll find the exact same consequence. So say we start our motion going in this direction, so directly towards the right, okay? And after 1 second, the other motion I get is this one here, VB. If I want to actually look at what's actually occurred, the actual change, remember, so the change in velocity is given by where you are at the end, subtracted by where you were at the start. So this is a nice vector diagram again. If you look at this, VA, so the change in velocity is VB minus VA. So how can we connect these arrows together? Well, have a look at this. VB is a positive vector, so it keeps its original motion, okay? Oh, VA, sorry. VA is negative, meaning by this arrow needs to be reversed to the opposite side. So I can draw my arrow of VA coming in like this. Negative VA. Which means the resultant vector is pointing inwards like so. So that's the actual change in velocity I'm experiencing when I compare the motion of VA to VB. So that's what we see here, okay? Just for simplicity's sake, I'm going to also list that out on here again. So this is the triangle that I can see to show the change in velocity. And then I can find a little angle, okay, of representing the two distances. Well, what I can actually find is I can actually compare it with this triangle up here. Exactly the same idea. If you actually have a look, these are two similar triangles. We are measuring the same angle, essentially. Okay. We have theta, and over here we have the overall displacement. So we have two similar triangles. We can actually derive and work out acceleration from here. Okay, so I've just redrawn the triangles that we had before. Okay, so delta V, or the change in velocity, is equivalent component of this triangle as the displacement of the triangle if we're looking at displacement only. Okay, so I can rewrite the equation like this. I can say that delta V is a ratio with one of these velocities, and that is also the displacement in ratio to one of these radiuses. Okay, so this process can actually help us derive the equation for centripetal acceleration. So multiply both sides by V, so I want to get rid of this V here, and divide by T. Okay, that'll give me this equation here. Delta V divided by delta T equals to V squared over R. Now, what you can actually see in this equation here is this bit. You have change in velocity over change in time. This is acceleration. So this formula here, V squared over R, actually represents the centripetal acceleration we've been looking for. Okay? So that's how you do this derivation. This is the equation you're looking into. Again, I'm not going to go through the questions in this video. I'm going to do a separate video to do these equations. So I'll see you in that one there. And the last derivation we need to do is centripetal force. So we know the acceleration. Now we just need to work out what the force is. And as you can actually see, all these different motions, circular motions that we see, that is, have different types of forces or centripetal forces. If we have a person throwing the ball here attached to a string. The centripetal force is contributed by the tension on the string. If we're driving a car around a roundabout, the centripetal force is contributed by the friction force. And if the Earth is orbiting around the sun, the centripetal force causing this is the gravitational force from the sun. So you can see, again, like we said, centripetal force is a resultant force. Okay, so let's try and derive centripetal acceleration using Newton's second law of motion, and that is the net force is equal to mass times acceleration. So when an object is moving in a uniform circular motion, the net force is the centripetal force, okay? Again, centripetal force is a resultant force, or, if you like it more, you can call it the net force. It's not a real force. Really remember that. Okay, so substitute that in. A is v squared over r. So substitute that into the equation. I get this. This equation represents centripetal force. You have mass in kilograms, velocity in meters per second, or speed in meters per second if you want to put it that way, and radius in meters. And so these are the three equations that we can look at to describe circular motion. What you can see here is if something is moving at a really high speed, that will increase its centripetal acceleration. If the object has to travel a really wide radius, it will have a lower centripetal acceleration. Okay, so these are the elements of the equation that we can look into. All right, so what we're going to look at here is a couple of past paper questions on multiple choice. So I know we talked about I wouldn't go through the calculation components, but I will go through the multiple choice questions in this PowerPoint. Okay, so the question we have here, which of the following diagrams correctly represents the forces acting on a satellite in a stable circular orbit around Earth? Fg means gravitational force, Fp is propulsional force, Fc is centripetal force, and then Fr is reaction force. Okay, well, the first thing is centripetal force cannot be. Okay, the reason why centripetal force should not be represented in this response is because it's not a real force. Really keep that in mind in your explanation, okay? Because centripetal force is not a real force, that's not the reason why a satellite orbits around the planet, okay? We have the reaction force, we have propulsion force. Now, here's the other thing. If we have a reaction force or propulsion force, it means we are applying a force in the direction of motion for our satellite. For uniform circular motion to occur, a stable uniform acceleration or stable circular motion to occur, there is no change in speed in its tangential motion. So the speed here, this speed here, is constant. So if we have a constant speed in that horizontal motion, there shouldn't be no forces, or no forces should exist, which means D is the correct answer. This is the only one that really truly represents how the force of gravity is pulling the object in. And this is correctly demonstrating that the tangential velocity is constant. Okay, I might not draw that out there so not to confuse you with the force, but this is the correct reasoning. All right, next one, B. We have a 200-gram mass swing in a horizontal circle as shown. It completes a 5 revolution in 3 seconds. The circle has a 2-meter diameter. Which of the following forces is closest to the required to keep the mass moving in this circular motion? Okay, so what we have here, we need to firstly find out the period that it takes for one revolution to occur. So I know that there are 5 revolutions that occur in 3 seconds, okay? Which means I can work out, in 3 seconds, how many revolutions do I get? So I have 3 seconds and I went through 5 revolutions. So that's 0.6 seconds for one revolution to occur. Substitute that into your centripetal force equation, mv squared over r. Okay, so know that the overall velocity of this particular motion is, let's see. Okay, so I know also the velocity of a moving object is 2 pi r times t, right? That's kind of the idea that we have. So I can substitute this equation into this equation that we have here. So it's mr times 2 pi r t squared. Okay, if I readjust, okay, because I don't have velocity here, what you could do is you could substitute the numbers now, or you could cancel everything out. Okay, so just for simplicity's sake, I'm just going to show you what the equation ends up looking like. This is the equation we end up with. So this r square here is going to become r because it cancels with this r here. And then everything is sort of already there for you. So the final equation you get is 4m pi squared times r and over t squared. So it's 4 times 0.2 because that's 200 grams. Convert that into kilograms. Pi squared times 1 over 0.6 square. And so the answer we get is 21.9 newtons. So the closest to that answer is D. Okay, and so that is how you do the question. And that also concludes our lesson to explain for the forms of uniform circular motion. If you found this video useful, give it a like and subscribe, and I will see you next time. Thank you for joining.